Alright guys, so we're going to do the polar coordinates. Now, let me just say that you might want to pause this, go back into your canvas, and underneath there should be a link that says polar graphs. Now yes, you can sketch these out yourself, but we all know that when we do a graph, it's easier to graph it when it's perfectly out. So these are the polar graphs that you want to use. Again, it's a PDF file that's going to be the link under where you found these videos on the home page of your canvas. Okay, so let me continue. In addition to the Cartesian plane, so x comma y, that's our regular graph we've been using, and the complex plane AB, there is another coordinate plane called the polar coordinate system. The origin of the polar coordinate system is O, which is the pole. So think of it when you think of a Cartesian plane, it's your point 0, 0. The pole is the endpoint of a ray called the polar axis, which extends to the right, as you can see down below here. At point P on a polar coordinate system is represented by r comma theta. So r being your radius, but theta being your degree. Where r is the direct distance from the pole, O, to the point P, and theta is the angle of rotation with the initial side of the polar axis. Okay, so it's always going to start here. And terminal side segment OP. Just like trigonometry, positive angles rotate counterclockwise from the polar axis, so counterclockwise, and negative angles go clockwise. Alright, so I'm going to show you how to plot a polar coordinate. So like I said, it would be easier having the polar graph. Okay, now what I did in this first one right here is I labeled our O, and I did our 90, 270, and our 0, 180, so I can see. Before we go into graphing, let's talk about what these angles are. So if you count up all of these angles here, we should get 24 of them. So if we take 360, which is the whole circle, divided by 24, we get that each of these coordinates of mine are by 15 degrees. Okay, this is good to know, because when I actually put my angles down, I'm going to label on which angle it's supposed to be. Now, not all graphs, just like when we do a Cartesian plane, we don't always have to go by ones, or when we get a graph we can go 10 by 10 or 20 by 20, so on and so forth, right? You don't have to go by ones, you can go by twos, you can go by halves. Well, here, I mean, really, this graph is going by 15 degrees, but we could go by 30s. Now, why would we go by 15? Well, because 15 captures 30, 45, 60, 90, so on and so on. If we only went by 30s, we wouldn't capture the 45, so we need to make sure that we can use the same graph throughout this whole thing. All right. So let's see, our first one that we're plotting is 3 comma 2 pi over 3. Now, usually when we graph something, we do like x comma y, we do the x first, then the y, so on and so forth. And you can do that here. You can do the 3 first by going out 3 and then doing your degree, but you'll find that in future questions, you're going to want to actually do the degree first and then move out. So when we do our degree or our theta, right, we're going to do that first according to 0. We're going to move to that angle, and then we're going to move outwards how many our r is. Okay, so we're going to do our theta first. So if you look or remember from your unit circle, 2 pi over 3, and we're going by 15. So 2 pi over 3 is right here. Okay, this is 2 pi over 3. I'm just highlighting in the whole thing so you can see where we're at. But now we know that our r is a positive 3. So I'm going to go out 3. 1, 2, 3. And I just went out 3 of those circles. So this is where the coordinate 3, 2 pi over 3 is. Our next coordinate here is going to be 4, negative pi over 6. Again, I've been showing you guys here that we want to do the degree first, the theta, and then move out. Well, negative pi over 6, so let me label the 90, 270, and the 0, 180 right now. Now, negative pi over 6, that means that we would be down here, right? Because we have to go clockwise. Okay, and then we're going to go out 4. So 1, 2, 3, 4. All right, in our next one we have negative 2 pi over 3. So let me mark down my, almost like my x and y axis there. Okay, now in this case, again, we're going to do pi over 3. So pi over 3 is going to be right here, right? Now, the thing is, though, in this case, we're going negative 2. So instead of going 1, 2, we're actually going to go backwards. Think of a number line. Instead of going forwards, we're going to go backwards. So I'm actually going to go on the same line. So if I see, like, backwards, backwards would be over here, right? So I'm going to go negative 2. So backwards to 1, 2, and there is my coordinate. All right, so next, we discussed about how rectangular coordinates x, y has exactly one representation. So if I did the point negative 2, 1, there's only one spot that I could do negative 2, 1. But if you look at a polar coordinate, it can be represented in infinitely many ways. So I'm going to show you that right now. So negative 2 pi over 3, right? We have it right here. But if you look, we actually can do another coordinate there that ends up in the same spot, especially since we keep going around and around and around. So like, let's mark it as 2, 4 pi over 3. All right, that means if we go to 4 pi over 3, and 4 pi over 3 is down here, and then we go to 1, 2, what do you know? We're in the same spot, even though I had 2 different coordinates. So 2 different coordinates, but same position. So with polar coordinates, we're able to do multiple, infinitely many different coordinates can get you in the same position. It's almost like our unit circle where we can go around and around and around. All right, let's go to our next page. So just like on our unit circle, how we could get to multiple representations getting the same angle or the same position, we can set up equations that allow us to happen like this. So r comma theta can be represented as r comma theta plus 2n pi, n being an integer. So 0 would just give me theta, 1 would be theta plus 2 pi, 2 would be theta plus 4 pi, so on and so forth. Now, if we're dealing with r comma theta and we wanted r to be negative, we take theta plus pi plus 2n pi, so depending on what n that is, things like that. So we need to talk about going forward, going backwards, and let's see what we can do with this. So for each of these coordinates down here, we are going to represent it in a different form based on that r is going to be positive or negative and what interval we want it to be on. So the first thing, guys, I'm going to do is I'm going to take my graph and actually graph this coordinate out. So we are going to do our x comma y, and we are doing 3 comma pi over 4. Alright, so when I graph this, I go pi over 4, and then I move out 3. 1, 2, 3. Let me label that in purple to keep it consistent. And that is the position I want to be in. Alright, so now let's make new coordinates that end up in the same position. So let's see what we have. Okay, it'd be nice if I can still, let me fold this, maybe we can get that one graph as I do the work. Oh, that works out pretty nice. Okay, so we want it where r is still positive. Well, that means that r is still going to be 3. Okay, but now we want it in the, it to go around within 2 times, right? Because this is 2 pi, but we want it to be between 2 pi, so it's double around. So if we double around, that would be our theta, which is pi over 4, plus n would be 1. So if I actually put that together and I do my math correctly, I get 3 comma, well, 2 pi, that changed it into 4, so would be 8 pi over 4, so I get 9 pi over 4. So this is 2 pi, that's 8 pi over 4, and that's the pi over 4. Okay, now let's look at the other one. On the next one, it wants us to our r to be negative, so we're going to have negative 3 instead. Now we want to talk about our theta, right? If our theta is pi over 4, now if we want to go negative, remember we add pi first, and then see what happens there. So let's try that out. And remember, I want to end up in this position, right? I want to stay right there. So if I go pi over 4 plus a pi, I'd be down here, right? Or on this line. And now if I go backwards 3, do I end up in the same position? I do. So I don't need to add anything on. If I added like a 2 times 1 pi, I'd be going in another round, which means I would be going between 2 pi and 4 pi. But I just want to be between 0 and 2 pi. So let me add this up, and I'm going to show you again how this ends up in the same coordinate. So we get negative 3, comma, pi is 4 pi over 4, so that would be 5 pi over 4. So let's check that out. If I go to 5 pi over 4, I would be right down here. But then I'm going negative 3, so I'm actually going backwards 1, 2, 3, and I'm in the correct spot. Alright, the next one is, we have our r is still the same, so it's positive. Now, here's the tricky part. what makes us go backwards? Well, what makes us go backwards is a negative radian, right? A negative degree. So, because 0 to negative 2 pi is clockwise, so let's start with our pi over 4, because that's what we start with, our theta. But if you think about it, instead of adding 2 pi, we're going to add 2 pi times negative 1, because we want to go backwards. And if we think about that, that's really nice, because that's 8 pi over 4, negative 8 pi over 4. So that brings us to 7 pi over 4. And the thing is, it is a negative 7 pi over 4, because that was negative 8. Well, let's see if that's correct. If I want to go negative 7 pi over 4, well, remember, that would be 7 pi over 4, which is down here. And because we're negative, we reflect, so we're right here. And we go 3, and we're in the same position. Okay, so if you want to go negative, if you want to go negative 2 pi comma 0, all we have to do is add a negative 2 pi to it. Okay, guys? Let's take what we learned right now and see if we can contribute that to the next one. So, first one, we're going to keep r positive. And now we want it between 2 pi and pi over 4. So we get 2 pi over 3 plus 2 times 1 pi. If we simplify that out, we get 5, comma, and then let's see, so that would be 6, 7, 8 pi over 3. And we can graph both of these and see that they are in the same position. Next one, we want a negative r. And since we want negative r, we're going to take our theta and add pi to it. This gives us negative 5. Let's see, that's 3 pi plus 2 pi is 5 pi over 3. And for our last one here, keep r the same, but we're going to go backwards. So 2 pi over 3. And then I'm just going to combine that, guys, and put that as a minus 2 pi. So hopefully I get a negative, right? So I get 5, comma. Well, 2 pi changed into 3. That would be a negative 6 pi. 2 and negative 6 is negative 4 pi over 3. Again, you can check your coordinates to make sure that these 3 coordinates and this one right here are in the same position. Alright, down below we talk about relating. What we're going to do is pretty much convert rectangular, which is the Cartesian, and polar. So what they want you to do, guys, is to relate it back to your unit circle. The reason why is we want exact answers. So you should not be able, or you should not have to, use your graphing calculator. You should be doing it exactly. So you want to keep your unit circle in mind. Okay. I'm not going to write down the unit circle because you guys should have that down. All right, let's talk about the relationship, though, between our polar and our Cartesian. So we have that r comma theta and x comma y, but how do they relate, right? How can we get x there? Well, let's remember our trig functions. If I want x, and this is theta, or if I want y, theta is, here's x. X is adjacent to theta. And r, because we want it in relationship, r is the hypotenuse. Well, what trig function does adjacent and hypotenuse? That is cosine. So I can write out the form of cosine theta equals x over r. Now again, remember, I'm going to then convert that. I want to convert this r comma theta into x comma y. So I have to solve for this x. That tells me that x is the value of r times cosine of theta. Same thing, if we were to solve for y, y is the opposite of theta, opposite, and then we have our r being hypotenuse, so we have sine of theta equals y over r. So that allows us to know that to get y, we do r sine theta. So this allows us to go from polar to rectangular. So I would note that, guys. This is to convert polar to rectangular. Okay, so what about going backwards? What if we had x comma y and we had to get your r theta? Okay, so this is rectangular to polar. Well, let's think of this. If we have an x and a y, how do we get r? So we have an x, we have a y, how do we get r? Well, think about it. That is, here's two sides of a right triangle and we need the third. So to get r, we think of the Pythagorean theorem. So to get r, we use the Pythagorean theorem. Now, how do we get theta? Well, if you remember, we have an x and we have a y. So how can we get theta? X, y, theta. X, y, theta. Ooh! Opposite? Adjacent? Well, what's opposite and adjacent? Tangent. So tangent theta equals y over x. Now, keep in mind, your theta is going to be based on what quadrant you're on. Okay, so be careful with that. Because when we do inverse tangent, we have to think of the first and the fourth quadrant, which is fine. But then also we have to relate it back, where is our point actually at, okay? All right, so example 3 here. We're going to go rectangular to polar. So we're going to use this top half here, okay? All right, so we get 2, 5 pi over 6. All right, so r is 2, theta is 5 pi over 6. So x is 2 times cosine 5 pi over 6. Now again, remember how I talked about we need to use our unit circle to get exact values, not the calculator. Okay, so 5 pi over 6, looking at the first coordinate because it's cosine, would give us, keep that 2 in front, and that cosine 5 pi over 6 gives us negative square root of 3 over 2. So that reduces this answer to negative square root of 3. Now let's do our y. We get 2 sine 5 pi over 6. Well, sine 5 pi over 6 is 1/2. And this brings us to 1. So our rectangular coordinate is negative square root of 3, comma, 1. Not that bad, right, guys? Okay, let's do it one more time. Make sure we have this down. So r is negative 4. Theta is 4 pi over 3. So x equals negative 4 times cosine 4 pi over 3. So think of our unit circle. We get negative 4 times, well, cosine of 4 pi over 3. Right? 4 pi over 3 is negative 1/2. So we get positive 2. Y is negative 4 sine 4 pi over 3. So that's negative 4 times negative square root of 3 over 2. Reduce that, we get 2 square root of 3. So our rectangular coordinate is 2, 2 square root of 3. Sorry guys, my coworkers keep messaging me and I don't know how to shut it off right now. Alright, let's move on. Last one here. We are going backwards. So we are given the polar coordinates, okay? Or no, we were given the rectangle. We're given that x equals 3 and y equals negative 3. Now remember, at one point in this we have to figure out, hey, is it in the right quadrant? So if we look at this, 3, negative 3 is going to be down in the 4th quadrant here. Okay guys, so let's keep in mind about theta and everything like that. Okay, so first of all, let's find our r. Remember that r squared equals x squared plus y squared. Okay, we do this out, we get r squared equals 18. Take the square root. Now remember, we want exact answers, guys. So r happens to come out to 3 square root of 2. Okay, square root of 18, you have a perfect square of 9 in there. So I take the square root of 9, which is 3, leaving 2. Now I need theta. Remember, tangent theta is y over x. So think of this. Where is tangent negative 1? Where is tangent negative 1? It is negative 1 here. It is negative 1 here. And of course, which one do we want? We want the one down here, right? Alright, well, think of this. What is this degree right here? We're going clockwise, and since they are the same, right, 1, that means it's the 45. So theta is negative 45. So which means our polar coordinate is 3 square root of 2, comma, negative, of course, I don't want to do negative 45, right? I want to do pi over 4. Okay? Because I want it to be in radians. So let's redo that. There we go. Okay, I know this is going to keep hard to get used to, but you need to know which way is what and what formula you're using. So here we have x equals negative 6, y equals negative 2 square root of 3. Alright, this tells me that we are in the 3rd quadrant, right? Okay, so let's find r. R squared equals negative 6 squared plus negative 2 square root of 3 squared. Okay, you guys can do this in a calculator if you want. Just remember the squaring of square root of 3 is 3. Okay, so I get that r squared equals 48. Take the square root and reduce it. I get 4 square root of 3. Okay, 16 goes into 48 3 times. Square root of 16 is 4. Now, tangent theta equals, and we do our y over our x. Now, before I look at my unit circle, guys, what I'm going to do is actually reduce this into something that would be on the unit circle, easy to identify. And as you can see, this reduces to the square root of 3 over 3. Okay, so square root of 3 over 3, if you talk about the inverse, right? Inverse of tangent means that I have to be in the first or second quadrant, right? So square root of 3 over 3 would be pi over 6. Okay, pi over 6, so right over here. But the thing is, we don't want to be over there, right? We want to be here. So what do I have to do to pi over 6? I have to add a whole pi onto it. Okay, because think of this, the inverse tangent, so I'll write this down so you can see it. The inverse tangent of square root of 3 over 3 equals pi over 6. Okay, because it can't be in the second or third quadrant. But because we want to be in the third quadrant, I have to move this to the third quadrant by doing what to it? I need to add pi. Well, pi in sixes is 6 over 6, so 6 pi over 6, plus another pi over 6 means that theta is going to be 7 pi over 6. So our polar coordinate is 4 square root of 3, comma, 7 pi over 6. Again, one of the biggest things to watch out for is to realize where your coordinate is supposed to be. Our coordinate -6, -2 square root of 3 is in the third quadrant. So when we make our polar coordinate, it has to end up in the third quadrant. All right, good luck.